Yeah, so good morning, everyone, and welcome once again to Fei. And today we have the hands-on session using test data, which Fei is going to conduct. And Fei, I think we'll have to let people interrupt, right, in case they have some issues.
Yeah, of course.
Yeah. So today, in case anybody has any issues, you'll all have permissions to unmute yourself and ask questions because you should hopefully do things while they are being run, right? So, and you can also raise hand. You know the raise hand option. Look on reactions button. You can do raise hand, or you can also use the chat window to write your questions, right? So we'll be monitoring that, and so we'll start off. Yeah. So take it away, Faye. Yeah.
Sounds good. Thank you, Priya.
Yeah.
Hi, everyone. Welcome to the second section on the test mission. So as promised yesterday, we'll first take a look at the first discovery paper from TESS. And we're going to move on to some hands-on session to look at how the test data for this object is processed for planet discovery. Hope everyone had a chance to look at this paper. If not, let's walk through it together. So the title of the paper is Test Discovery of a Transiting Super-Earth in the Pi-Mensei System. So for those of you who are not familiar with astronomical naming system, Mensei is basically the constellation in which the system is discovered. Usually the brightest star in one constellation is called the alpha of that constellation, followed by beta, etc., until you run out of Greek alphabets. So pi is probably within the 20-something most bright star in the Mensei constellation. So this paper is led by Chelsea Huang, who I think is a postdoc at MIT. She's in charge of reducing the test data and organizing planet discovery. And there are a bunch of other people who are the core science team for TESS, as well as other collaborators who contributed to some extent to this paper. All right, let's move on to the abstract. So usually the abstract of a paper is a quick summary of a paper, reporting some of the highlights or the key parameters for a system. For example, here, for Pi-Mensei system, it is a really bright star with a visual magnitude of 5.7. So for those of you who are not familiar with astronomical magnitude, I'm sorry? Is there a question?
Sorry, I think no, that was an interruption. I'll just mute it. Yeah, go on. Go on.
Sounds good. Yeah, so the astronomical magnitude system actually measures the brightness of a star compared to some standards. I think one of the usual standard people use is the star Vega. So if a star is brighter than Vega, well, there are only a few stars on the night sky that is brighter than Vega. The magnitude goes down, but for stars fainter than Vega, the brightness goes up. And every change in magnitude by number 5, the brightness drops down by a factor of 100. So this star is roughly about 100 times fainter than Vega, but that is still a very bright star. So for naked eye observation, if we just use our eyes to observe the stars, we can see up to magnitude of 6 or so. So this is one of the very few planet hosts where you can actually see it with your naked eyes. All right, so this system actually had a known planet before from radial velocity measurements, which is a giant planet on an eccentric orbit, and with a orbital period of 5.7 year orbit. So this is a system where this is a planet very much like our Jupiter. And what is new here in this paper is that if you take a look at the TESS light curve for this system, there's actually a closer in planet with a radius of about 2 times that of Earth, an orbital period of about 6 days that shows transits. And by measuring the transits, the author were able to figure out both the period and the radius of the planet. And with that transit discovery, the authors actually went on to look at the archival radial velocities more carefully. And since they know the orbital period is around 6 days, so they can look for the signals of this smaller planet in the radial velocities more carefully or more specifically at that 6-day periodicity. And what they found is that they can actually use the mass, use the radial velocity to constrain the mass of that inner planet. So the importance of this system is that, as I mentioned earlier, it is one of the very few stars hosting a planet, but are also visible to the naked eye, meaning that the host star is really bright. And this makes the planet amenable to a bunch of follow-up observations, such as atmospheric spectroscopy, asteroseismology, which is, I don't think I mentioned this yesterday. Asteroseismology is basically measuring the oscillation on the host star, and the mode of the different oscillations actually encode a lot of information about the host star, including its mean density, its age, its chemical makeup, etc. Another possibility is to perform the so-called Roster-McLaughlin effect. This effect happens when a planet or a star transit another star. So as the star or the planet's shadow moves around on the host star, it actually blocks sometimes the red-shifted or the blue-shifted limb of the host star, therefore breaking the degeneracy between the redshift and blue shift, causing an anomalous effect you can measure in Doppler effect. And this measurement can really tell us about the orbital orientation of the planet. As geometry, I don't think I mentioned yesterday either, is basically the measurement of the coordinate of the star over time. So as we know, when a star has a companion, say a planet or a companion star, both of them will execute Keplerian motion. And that Keplerian motion can be seen as geometric measurement. And from there, you can measure the mass of the both stars and their separation. And for direct imaging, that's easy to understand. It's if you look at the star with adaptive optics, meaning that you remove much of the atmospheric turbulence to achieve high angular resolution, you can potentially see the light from the companion giant planet directly. All right, that was a quick summary of the paper. Let's maybe walk through some of the key plots in this paper. So this first figure, we're actually seeing the so-called postage stamps, or a cutoff of the CCD where the star Panmansei is located on the right. I think we showed this yesterday in my talk. So you see the grid patterns, these are actually pixels on the CCD from the detector. And this cross actually marks the expected center location of Panmansei. And you can see the light from the host star actually spread out into many neighboring pixels. This is usually because, first of all, there's something called the point spread function for the optical systems on a spacecraft. Usually this means even for a point source, the resultant image wouldn't be like an infinitesimal point source. It usually adopts the shape of an airy ring, which is diffraction limited. So the size of this airy ring actually is related to the wavelength where you're looking at the star, as well as aperture of the lens you're using. So for a smaller aperture, which is what we use on TESS, 10 centimeter, this point spread function can be pretty wide. So you have to sum over many pixels to quantify the brightness change of the whole star. But the trade-off is that when you use a large pixel, sometimes you run into the risk of including too much background noise. The sky itself is also emitting light, as well as if there's neighboring stars or galaxies in this field of view, those light will also contaminate the brightness measurement you could do. So there's usually a compromise on the exact size of the aperture used. Well, by the way, the aperture is just a set of pixels that you use to sum to represent the brightness of the whole star. And that is shown in the red silhouette here in this figure. All right, moving on to maybe the second plot in the paper. So here we're seeing the so-called light curves. The upper two panels are both plotted in terms of time versus the brightness of the whole star. So time here is showing this somewhat weird unit system, which we call barycentric Julian date, minus a very large number. So barycentric Julian date, or Julian date, is a convenient timing system astronomers devised. I think the starting point is something like 4700 BC. So this timing system hopefully will capture any sort of astronomical events that's ever recorded in history. So if you look at world history, I think the major civilizations arise somewhere during that time, like minus 5,000 years. So this timing system can help us just put every possible astronomical event on the same footing. And if you calculate that time in terms of number of days, it's roughly 2 million days. So you can put any dates more or less in human history into this timing system. That's why there's a big offset. So for TESS measurements, I think the measurement only happened for something like 30 days here, as you can see. So the upper plot shows a so-called raw light curve from TESS. This light curve includes both the stellar variation, the transit signal, as well as systematic effect from the spacecraft. So you can see this dotted line here. These actually represents when the spacecraft performs some sort of momentum down. In other words, the spacecraft is changing its orbit slightly to correct itself into the correct orbit. So after the momentum down, you can see that there's some pattern in the light curve. For example, you can see that immediately after the momentum down, the brightness goes up a bit before it slowly drops down. So we know some of this variability is due to the spacecraft itself. So we can do some tricks to remove that variability. This usually involves some sort of fitting. One prominent method is called the spline fitting. I believe the second panel is after removing the the spacecraft schematic. Now the variation is more or less only due to the transit of the planet. And you can actually visually see each transit event of the planet. These are the dips we see here. So this dips actually turns out to be very periodic, meaning that the signal is probably from capillary motion of the planet. And what you can further do is so-called phase folding, which is changing the time axis of the light curve by taking the modulus of the orbital period. If the planet executes perfect capillary motion, then this transit should always occur at the same interval, and they phase up really well, like shown in the bottom panel. And by modeling this shape of the transit light curve, we can figure out how exactly the planet is transiting the whole star. For example, the size of the planet, as well as potentially the eccentricity of the planet, as well as so the so-called impact parameter of the planet, In other words, did the planet transit across the stellar equator, or did it transit, say, the 30-degree latitude of the star, or did it transit only the polar region of the star? So these can all be modeled from the transit line curve. We'll do that later in the Python notebook.
Hello? Hello? Hello?
Question? Go ahead. We can hear you. Okay, was that a question, or was that just checking the?
Do you have a question? No, I think some of them log in with their
Hello?
this thing. Yeah.
Yeah. Here in the plot, there is a negative flux deviation. What does that negative flux deviation mean?
Right. So, as I explained yesterday, we are only counting the number of electrons, right?
Okay.
So, first of all, there are at least a few effects. First of all, this measurement is not perfect. So sometimes the number of electrons, well, we are counting the number of electrons, but there's a whole bunch of amplification or analog to digital conversion that the CCD has to perform. And during that mathematical operation, sometimes a negative value is introduced. So amplification is basically just increasing the number of counts to something more reasonable. Analog to digital conversion is basically converting the real systems, the number of electrons, to a binary number that we can register in computers. And the third effect is that we are only interested in so-called relative flux level. We do line curves. This is because there can be a lot of systematic effect, or the stellar variability can change on longer time scale. So we want to remove those as much as possible. So the way we do it is actually to normalize the flux level by some mean or median. So you subtract away a constant value, then the flux can be negative.
Okay.
Yeah. Sounds good. Very nice.
Yeah, thank you.
All right, the third plot of this paper, let me zoom out a bit. So the uppermost panel shows the so-called radial velocity measurements across time. Again, the time is quoted in BJD minus some offset. So the immediate thing that jumps into view is that there's some large scale curvature that can have amplitude of up to 300 meters per second. And this curvature seems to be repeating itself over, say, maybe slightly more than 2,000 days. So this is the radial velocity curvature caused by that giant planet we know on 5.7 days. So the lower panel here on the left actually shows a phase-folded variation from that giant planet. And you can see the black curve is a Keplerian model to that curvature or to that variation. And when a planet is on a circular orbit, this variation will be a perfect sinusoidal wave. But if the planet is eccentric, then this curvature will deviate from the sinusoidal shape and have a more peaky shape, as shown here. So this giant planet is known before the TESS mission. The new thing here is that if we take the so-called periodogram, which is, again, a method for searching for sinusoidal signals, and you can try this search at a various period grids. For example, here, the period grid extends something to maybe half a day to a few hundred days. And at each trial period, a sinusoid is fitted to the radial velocity measurement. And the amplitude here indicates how strong that signal is detected. And in this case, if we take a look, The transiting planet orbital period 6.26 days shows a really strong peak in the periodogram, indicating that the transiting smaller planet is also seen in the radial velocity variation. While this is perhaps less convincing if you look at the bottom right panel, this is phase folded at that 6.26 period. And you can see the individual measurement uncertainty on the various instruments can be quite big. But if you bring all of them down, given the large number of data points, you can actually make out a small trend, a small sinusoidal trend that corresponds to the inner planet. So this radial velocity detection and the transit detection together actually makes the status of the inner planet quite secure. So this plot, I think I'm gonna skip it because this is basically showing that the various individual transits are not caused by some systematic effect. Rather, they are more conforming to the expectation you have for transit shapes. And this histogram actually shows the transit depth or the planet to star radius ratio for the individual transit. And you can see they agree more or less with each other. So I want to spend some time on these two plots. So these two plots are showing us the significance of this inner planet discovery. The upper panel shows the planet size versus the apparent magnitude of many of the exoplanets we have discovered. And the symbol side, I think, represents how strong or how favorable that planet is with regard to transmission spectroscopy. So yesterday we mentioned transmission spectroscopy will allow us to quantify the atmospheric composition and as well as thermal pressure relationship of that atmosphere. So a brighter planet or brighter planet host will provide us more photon for this measurement. So that's why these apparent magnitudes, this low apparent magnitude stars in the upper side of the plot provides systematic larger symbols. The other consideration is that for larger planet or planet with lower densities, you expect a more tenuous atmosphere on those planets. And those more tenuous atmosphere will also provide a larger signal when you measure the transmission. So in short, these few planets in the upper left corner are the most favorable planets for transmission spectroscopy studies, especially with the upcoming JWST spacecraft. And Panmasis C, which is the inner planet, actually is maybe the top, maybe 5 planets that is discovered so far. So a lot of time would be dedicated to study this planet. So the lower panel shows the mass radius of Panmasis C. The x-axis is planet mass in Earth masses, and radius is on the y-axis. So the gray symbols are other known planets, and Panmasis C is shown here in the red symbol. I think the opacity of the various points actually correspond to how accurate that mass radius measurement is. So you can see also plotted here are theoretical mass radius curves for a bunch of compositions. For example, 100% iron, Earth-like composition with 30% iron and 70% magnesium silicate. 100% magnesium silicate, a purely rock-based planet, as well as a water world with 100% water. And this 1% hydrogen helium actually assumes that you have an interplanetary core of Earth-like composition on this green line, but on top of which you also put on 1% by mass hydrogen helium atmosphere. So if you look at Panmasis C, that's roughly 5 Earth masses at about 1.9 Earth radius, or right about 2 Earth radius. So this planet actually has some degeneracy in its composition. It can be either made up with some amount of water on top of like a more Earth-like core, or the other possibility is it may be made of more iron-rich core on top of which you have some amount of hydrogen helium envelope. So this degeneracy cannot be broken by just looking at the mass radius curve. You have to go out there and do this transmission spectroscopy study to look at the atmosphere. And this is, I think, what the community is going to do in the next few years for this planet. Yeah, also, maybe I should point out some trend here. If you look at Earth and Venus, as well as some other exoplanets, the really well-measured ones really do cluster around Earth-like composition. And the same trend was seen in the so-called contamination of white dwarfs. So some of the sun-like stars, when they evolve off their main sequence, they will become white dwarfs, which typically have the size of the Earth. And now on those white dwarfs, if those white dwarfs have some orbiting planet that is tidally broken down, and some of the planet rocky material gets absorbed onto the white dwarf surface, you can actually see those white dwarf, those debris or those rocky materials detailed composition by studying the white dwarf's spectrum. And those studies show that many of the debris surrounding white dwarfs are also Earth-like, with substantial amounts of magnesium silicate as well as iron. So the community is more or less converging to this understanding that maybe the exoplanets are all quite similar to our Earth. Well, there are some other outliers too, but for larger planets, the so-called mini Neptunes, things are less certain. It can either be made up with water or some amount of hydrogen envelope. So this is still actively being researched. And Pymon's AC is a perfect system to study that degeneracy. All right, I think that concludes a quick review of this paper. Let me pause here and see if there are questions from the audience.
Yeah, do we have any questions? Actually, at present, the questions are more about the installation. People are trying to install stuff.
Oh, okay, I see.
But we'll get to that later. Are there any questions about this material? I think you can go ahead because, like I said, once we give them stuff to install, people are all just trying to install stuff.
Yeah, sounds good. Yeah, we can always come back to
Yeah.
questions
Okay.
about it. So this is a notebook.
Wait, Faye, I'll just talk about a little bit of the problems which people are having with installation.
Oh,
So,
okay.
somebody says they're having a problem with the Batman package on Windows 10. How does it work on Windows? It's showing a PEP 517 error regarding the building of the wheel.
So I
But
don't use Windows myself, and I
yeah, but
know people using Windows and try to install Python packages on them can have problems. So one thing I may suggest is using this Conda environment, Anaconda.
yeah, no, I think we have a Windows machine also, so
Yeah,
we installed it over there. It's working fine. So probably that's what we asked them. Maybe they should update the Conda which they have
yeah.
to
So
see. Uh,
They asked quick reinstall button
yeah, so
to
that
use
so
for
so that's one thing. And the other question was that should they use Google Colab instead? If they use Google Colab, will that solve the problem?
so I didn't set up Google Colab myself. Actually, I've never tried it.
Okay.
Uh, but I'm sure someone in the audience may have it. Maybe some of the organizers knows
Yeah,
how to
yeah.
use.
So we actually do use Google Colab, so we can probably try that. No, Prajala asked, Anaconda install comes with packages. Yeah, but it comes with packages, but not these ones. These ones I
Yeah,
think are not there. You'll have to
yeah,
separately install these.
yeah. So the benefit of Anaconda is it controls your coding environment and set requiring prerequisites. Checking code version is really convenient in Anaconda. Uh, yeah, that's why people are using it so widely, I think, for Python purposes. Uh,
So
any other
you are also
questions?
using Conda, right?
Yeah.
Oh, okay. Okay, fine. I think you can go ahead because I think many of these pertain to, individual cases, which we'll have to sort later.
Mhm.
So probably we can proceed with this, right? Yeah. Okay.
Yeah, so I think the three non-trivial packages here are the Leica package, the Allen Fit, and the Batman package. I can briefly explain what these are. So the Leica package was written by, I think, Geert Berensten, who's, I think, a researcher at NASA Ames. I think this package helps us download the Leica, download the target pixel, do some simple detraining. Uh, it's really convenient, so you don't have to search the database yourself. Um, I know many people in the community uses it. So this Fit package actually performs gradient descent for parameter optimization. Um, and LM stands for, I think, Lavenberg-Marquardt, which is a particular algorithm for doing gradient descent in high dimensional space. We will later use this to fit the transit light curve. And the Batman package was written by Laura Kuiper. Uh, and this package, I think it performs a quick calculation of what the transit light curve will look like. I think we may have a plot here. Yeah, this is basically calculating the intersection between two spheres. The larger one represents the host star and the smaller one represents the planet. But the extra layer of complexity is that the star is link darkened, meaning that on the edge of the star appears dimmer. On the center, the star appears brighter. This is because for each line of sight, the amount of photons you see, uh, or the amount of how bright the star you see, depends on how far your line of sight penetrates the whole star. So for the center of the star, you line of sight penetrate quite deep into the whole star. You see a higher temperature interior. But for the limb, your line of sight only penetrates the very top layer of the whole star and sees a lower temperature region. This is much like you see the sunset when the sun is near the horizon. It passes through a lot of atmosphere on Earth. So this so-called limb darkening effect changes the brightness of the whole star, and you have to account for that in calculating transient light curve. And Batman does this really efficiently. All right. Uh, let's see, anything else I should mention here? Yeah, the other package are simply the NumPy, Matplotlib, and Pandas. I think most of you who knows about Python use this package pretty regularly. Okay, so the first step in this analysis is to download the so-called target pixel files, which we see in the first plot in Chelsea Huang's paper. And this usually requires you to know the name of your star, which is here, shown here. This is, I think, an internal designation for PyNaCD, a bunch of numbers, and it's shown here. So later I'll show you how you can look up planets of your favorites and find out what their tick number is, this internal number is, and go download their data yourself. So this cell tells us, okay, this light curve actually came from TESS. If you find a system that's being observed or has been observed by multiple missions, those will be shown up here. And you may want to treat the light curve from different missions separately because they have different kind of systematic effect. This is the tick ID, or the tick name of the time-and-space system. Okay, the first plot we can make, this so-called aperture photometry plot. So for comparison, let's go back to Chelsea's paper. This is basically the same plots shown on the right panel of the figure 1. But we have corrected for the rotation. Here, this is a cutoff near the star penmancy, and we can put on a default mask or aperture, which is showing the pink pixels, and we'll sum all the lights within this mask to represent the brightness on the whole star. But usually this default mask isn't really good. Another way we can do it is to use something called the median mask. This is setting a threshold where pixels above some threshold. Here is basically a percentile, 85 percentile. Any pixel brighter than that, we include it in the so-called aperture. For example, here, if you look at the default aperture, one of the really bright pixel in the upper part of the plot is missed. But if you use a median aperture, all the major pixels will be included. All right, so how do we actually move on from target pixel files to the so-called light curves? So the pixel files contains a lot of images like these, each taken with a time interval of 2 minutes. So every 2 minutes, the CCD detector on the star is read off to represent the brightness of the star within the last 2 minutes. So the data actually contains many plots like this, as each of them is separated by 2 minutes. So for each of the plots, you can sum up the pixels in this aperture to represent one data point here. And if you do this for all the plots across time, then you can measure the brightness, how the brightness of the star changes. And you can see this light curve does not look very constant. For example, after this data gap, there's a slow ramp up of the pixels, of the brightness. And here, I'm not sure what happens, maybe some instrumental effect. You can see the flux change a lot. In Chelsea's paper, they actually cut away all the data taken here, as you can see. All right, moving on. So one simple thing we can do is, since we know there's a planet here, we can actually phase fold the planet, the light curve at the known period, which is about 6 days, and we know the time of the first transit, and we can phase fold the light curve here. And this part where you see a constant dip, where the flux level is systematically lower compared to other parts, this corresponds to the transit of the planet. So before we move on to modeling, one extra step we have to do is try to remove these long-term systematic effect or stellar variability as much as possible. So in light curve, there's something called LC.flatten. This actually tries to remove the longer term variability in light curve. And you can see this light curve is much cleaner compared to this one. And if we do the phase folding, the planet signal is more obvious near the phase 0. Okay, so we cheated a bit in this first few cells because we started with a known period and the transit time of the planet. But in reality, we are doing the transit search. We do not know the period of the planet. So how do we do that? So this is done in something called the box least square method, or BLS in short. So actually found a schematic showing how BOS works. So the transit light curve to the first order, you can approximate the transit light curve as a bunch of dips separated by a constant time interval, the orbital periods. And the key parameters here are the duration, how wide the transit duration is, the period separating them, as well as the steps or the mean amplitude of the decreasing flux level. So the BLS method actually performs what is called the match filter. Here you have approximated the transit light curve at this box-like shape. And you can do a grid search in period, duration, and depth to see which sort of combination of these three parameters gives you the best fit to the data. And coming back to the notebook, this is done over this period. This is only shown over this period grid. So you try the match filter at a bunch of periods, and you also try out a bunch of different transit duration and transit depth. So you collapse those two dimensions, duration and depth, to represent a peak signal at each period. So at each period, you can plot how strong the signal is after searching through a bunch of depth and duration. So clearly here, you can see that there are a bunch of peaks in this so-called spectrum of parallelogram. And the strongest peak here actually corresponds to a period of 6.299 days. Note, this is slightly different from the reported period of 6.26 days. This is because the period grid we are searching over is not as finely separated. So we can't trust this period, but it's a good indication of where roughly that period lands. So the next step is to, okay, there may be a signal here. Is it a robust planet signal? So to do that, we actually have to model light curve more carefully. Here, writing a bunch of functions that actually computes how the transit light curve will look like given the Batman model. And the key parameters here are the time of the first transit, the orbital period of the planet to the star radius ratio, the semi-major axis of the planet, the orbital inclination, which quantifies how inclined that planet is compared to the sky plane. If the planet transits the equator of the host star, which is shown here, then the inclination is 90 degrees. But as the inclination changes, the trajectory of the planet can actually move up or down compared to the disk of the planet, the host star. Let's see, the eccentricity of the orbital motion, as well as this omega parameter, which quantifies how that eccentricity is orientated compared to the line of sight. And this U1 and U2 parameter are the so-called limb darkening parameters. This will quantify how dim the star gets if you compare the center of the star to the limb of the star, due to that limb darkening effect I explained earlier. And this F naught parameter is basically a constant flux, meaning the flux outside the transit has some constant level, and we don't want to quantify that too. Okay, so these two functions actually basically first sets up the Batman model, then try to predict the Batman model. So this is done in two steps because the first step, the first time you set up the Batman model is going to take significant time. And the next time you don't have to set up the model. All you need to do is to call the model. All right, moving on to the so-called residual function. So the residual function actually computes how different your model is compared to the actual observation. And the input of this function is the different parameters I just introduced earlier. So what the code is actually doing is try out different combination of the parameters for the planet motion and compute the resultant light curve and compare that resultant light curve to the actual observation. And you minimize the difference between the observation and the model. And by minimizing that difference, you can land on, by doing gradient descent, you can land on the best fit parameter set. So I won't go through the details here. This is basically solving the Keplerian problem, which is converting time to a location of the planet on the night sky. And this residual is basically the model light curve minus the observed light curve divided by the local uncertainty. And this plot result function is quickly to plot how the light curve looks like given the combination of parameters we have seen. All right, that was a bunch of definitions of functions. Now let's actually do the gradient descent. Here, we give the star's name to the code, the tick name, and we define a bunch of variables we're going to use or initialize. And this input function is the initial guess of the parameter. For example, the period we know from the BI search, as well as the timing, also from the BI search. And for duration of the planet, radius s, semi-radial axis, we can all guess an initial value. This doesn't have to be super accurate. The same applies for the ring darkening parameters. All right. So basically here is putting things into the correct variables. I think the key command here is basically this lmfit.minimizing function. So lmfit, as I explained earlier, is the so-called Lavenberg-Marquardt algorithm for doing gradient descent in high-dimensional space. And the input we here is basically a function for, we defined earlier, the residual function for calculating the difference between the model and the observation. And pfit is the initial set of parameters we put in. So by running this, the code will meander in the parameter space here, including orbital period, semi-radial axis, etc., until it lands on a perfect combination that minimizes the difference between the observed light curve and the model. And this is shown here. So the black points are the actual measurements from TESS for how the flux changes from time and say. And this right curve is the best fit from the Batman model after gradient descent onto the best fit values of the parameters. Visually, you can see not all the black points is gone through between the measurement and the right curve. This is typically due to the measurement uncertainty. So each measurement is not perfect. It has some amount of white, so-called white noise. At a longer time scale, you can see that the light curve is fit pretty well. There's no correlated noise. The residuals all cluster well, almost symmetrically between the curves, the best fit curves. And we can ask, okay, now tell us what are the best fit parameters that gives the best agreement between the model and the light curve. And you can see the various parameters here. For example, this orbital period value is now very much closer to the value reported in Huang's paper. This is now 6.26 instead of the 6.99 value we got from the initial BIS search. And you can also read off some of the other parameters. And it will tell you, for example, this one will tell you roughly how big the planet is. Yeah, I think that concludes the first very quick walkthrough of the test data. So I know this is already written out. I think something the viewers can try is to look for planets that you find interesting. There are more than 4,000 planet candidates TESS has discovered. So you can look for them here in the so-called ISO-FOB website. I'll send a link later. So you go to this website, it actually lists more than 4,000 so-called TOIs, test object of interest, or planet candidates. Well, table is taking a while to load, but the upshot is you can click on one of the system, and it tells you a bunch of information about that planet. For example, this one is a known planet 162b. And it also tells you the tick number. So you can actually replace the tick number we use in the notebook here. So here we have something 2611, and you can actually replace that system with a new system that you find interesting. You can download its Leica and do the same fitting exercise yourself. Well, there are more than 4,000 choices, so just pick maybe some planet that interests you most. Yeah, I think that was a quick introduction to test data. I think we have some time for questions.
Yeah, sure. Thanks, Faye. That was very nice. But now my question is that since your notebook has all the basic plots, right? Which are the
Yeah.
additional plots which they can do? Because they need to be writing some code and doing some stuff themselves, right? So,
Ma'am, I also have a question. Can I
yeah,
answer?
sure. Ask.
So, Faye, I was running the code, the default file that you had shared.
Yeah.
It's telling me first is what error I'm getting is it is not able to locate the input text file that
Oh,
you.
okay.
Yeah, right.
Okay. Sorry, I'll interrupt. Gitanjali, it's there in the mail. In the mail, I'd sent the input file. It's there in
Okay.
the input in the chat box also today. I've put it
Okay.
here again.
Okay,
Sorry.
and
Yeah.
And I've just put a tick number in the chat box. I was trying to do it for this is actually 1266 star is 1266 and it's TIC number I have put in the chat box. Somehow it has got two planets around it, B and C, right? So every time I run the code, even if I change B to C in the program up in the codes up there where I mean, at one point you've defined for planet B, right? The code is running for looking at transit curve for planet B. I changed it to planet C, but still it's giving me the time period for the planet B only. I don't know why.
So something I forgot to mention is you can put all the planet info in this input file.
Okay.
So the way I've written the code is that you can actually put in two planets here. Just one row for each planet.
Okay.
And the code will be smart enough to know, okay, here actually I put a number of planets, which is actually the length of the P parameters. And the code will actually loop for the number of planets and do them individually.
Oh, okay, right. So I'll have to do the change here. I missed that probably. Right.
Yeah, and if you want to get a pretty good initial guess for the planet parameters, just go to this ISO-FOB website.
Yeah.
And they have all the planet parameters included here. Pretend that you don't know it to such precision. You can just put a value close to it, and the code should be able to fit it likely.
Okay. And one last quick question is that when you do the pixel fitting on the top, when you do when you try to find the aperture mask, will the method that you've given here, will it work for any kind of TIC number or?
It should work pretty well. But one caveat is when a star is in a crowded field, meaning that it has neighboring stars. Say, look here, maybe there's another star here with similar number of pixels. And those pixels from the two stars can overlap. And in those cases, this simple method doesn't work. You need something more complicated.
Right. Yeah.
For example, if you know the coordinate of the stars really well,
Okay.
then you can separate them. But
Right.
for this quick analysis, I don't think that's necessary.
Okay. Okay. Thank you. Thank you.
Sure.
Faye, could you please cut paste the website for the test data on the chat screen?
Yeah, of course. And all these is public.
Yeah. And then there's another question, which is, I have Adrita Khan have a question. When you're using codes, do you usually write them on your own or do you use a pre-existing algorithm? I'm new to programming. Do you have any advice on it? Better understanding of Python?
Sorry, I was copy pasting the. Could you repeat the question?
No, so the question is two parts. Yeah, thanks. The question was in two parts. The first one is that do you write your code from scratch or do you use pre-existing algorithms? And secondly, for a beginner with Python, what would you suggest?
Right.
What resources would you suggest?
So I usually write my own code, but I'm also open to use all the publicly available algorithms or packages. So that speeds up the process a lot. So, well, the short thing is, the short way to put it is, you don't want to invent the wheels again and again. If there are publicly available codes out there, you can definitely use them, and it's usually well written, very efficient. And you can focus writing your own code for your own science cases, which is probably something different, and you wouldn't be able to find a code that does exactly what you want. And the second part is using Python. Yeah, I would definitely recommend using Python. It's a very popular code. There's a lot of packages and support out there. And it can almost do anything you can think of.
And one last question. For the more ambitious of the students, what further development of the project could you this thing? Like in this case, they will just run the notebook, right? But if the ones are more ambitious, what are the kind of things they can study?
So, right. So one thing I would suggest is maybe look through the entire TESS database and try to do the BI search yourself. So this has been attempted to some extent by the TESS team, but with millions of stars, it's really hard. I don't think they have done an exhaustive search.
Okay.
The other part is sometimes there's something called a single transit. So TESS only observe a patch of sky for 30 days. And some longer period planet will only transit once. And when the planet transits once, it can be easily missed by the BR search. So one thing the TESS team is recruiting citizen scientists to do is to inspect the light curves themselves and discover planet candidate that has been missed by the pipeline.
I think work like that has been done by some students, right? There was some media report on that sometime back.
Yeah, so there's definitely some effort on that, but I don't think it's exhaustive.
Yeah, definitely.
Yeah, and so those two will definitely produce some science results if it is done properly. But for more instructive purposes, I think some students may consider doing like a uniform modeling of all the light curve and report a uniform set of parameters. Or maybe search for planet they are most interested in, maybe say very short period planets. So the search grid currently I think only covers you half a day. You can search for shorter or more weird planets, things like that. Yeah, I think there's a lot of things that can be done with this data set. But I'm not sure it's on the right time scale or scope for undergrad research. It may take a lot of time.
Okay. So thanks a lot, Faye. Do we have any more questions? Okay. I don't see anything. So thanks so much. It was really nice having you, and thanks so much for participating. Thanks so
Yeah,
much.
it's my
Yeah,
pleasure to talk to
yeah,
you. And
yeah.
and,
Thanks
make
a lot. Yeah,
yeah. All right.
uh,
I'll
yeah,
sign off.
yeah. Bye bye. Bye.
See you there.
Yeah. And now we'll start off with Tim, our good old friend Tim Hamilton, who's here. And hello, Tim.
Hi, Priya. Sorry, I was having to find my mute button and get rid of it there for a second.
So nice to see you. How's everything? All good?
Thanks. Glad to see you and both of you actually as well.
Yeah.
And
And
all
we're
the rest
keeping
of
you,
you.
yeah, and we're keeping you up again, like usual.
Yes, in fact, I've been getting everything ready, and then my wife and I were watching a movie. Then I went on to bed, and then just as I was about to sit down, my alarm went off, which reminded me, by the way, don't forget 3 minutes from now. Oh yes, I came down and got me some coffee ready. So
Oh, wow. So actually, the earlier speaker was from California. So that's why we gave him the earlier slot so that now he can sleep.
you really are getting a very worldwide bunch of us here, then in all different time zones.
Yeah, trying to. But I think that is one of the biggest advantage of this online mode, right? Where we can have everyone. Yeah.
Yes, yes, I think that has been just fantastic for it there. In fact, I was enjoying seeing I got the end of his talk at least there.
Yes.
But